Hello. I will be talking a little bit more about how we practically assemble bottom termination components with minimal voiding. So we've talked about some process changes, some material changes. We know that materials aren't going to get you all the way to, no voiding at all. So we've been working on a bunch of different process strategies to get you closer to that minimal voiding limit. So a lot of this stuff we've kind of touched on in other presentations. But basically, QFNs are being used hugely across the industry, and it's just getting more and more prominent. So far, of all the approaches we've tried, no single approach is like minimizing voiding all the way to zero. So this is a kind of analog process. You're trying to get as low as you possibly can without messing up anything else on your board, or just reducing the overall voiding percentage, but also looking at the largest void and the size of the largest void and making that smaller as well. Because as Greg talked about, if you have a large void and your die just happens to be right above that void, you're going to get very bad thermal transfer, and I think very large voids are probably the worst thing to see in an assembly like this. So inherently, the issue is that solder paste is 50% flux by volume. So 50% of what you're putting down on that pad is going to try to go away during the reflow process. So when you have a large paste deposit like we have on the thermal pad of the QFN, or BTC, you have a lot of volatiles that are trying to escape through a very small space, and this leads to voiding, but it can also lead to sometimes bridging if you have too much paste, or as Greg was talking about with collapse, you can have bridging from collapse, or extra low standoff, which we'll also be looking at in this. So essentially the strategies I'm going to talk about today, several of them were kind of first researched by Dr. Lee and then other people. And I've noted a couple of the titles of the papers here in case you wanted to look at the really deep results. I'm just going to kind of touch on key points of the findings, and then after I go through each of the strategies, we'll talk about a trial that I did with a customer where they were trying to adapt these strategies to their assembly. So for thermal pad design, as Greg mentioned as well, there's a strategy to break up the bottom thermal pad into smaller either paste deposits, or in this case, smaller copper pads, so that you create venting channels to allow these volatiles to escape during reflow. So these window panes create the pathways to vent the volatiles out to the spaces on the edges by the small perimeter solder joints. So as you'll see going forward, the vent channels result in less large voids, fewer and less overall voiding. However, these venting channels that you're creating will actually count as voided area because they're discontinuity in the Z direction of the solder joint. So this was Dr. Lee's first crack at this idea of breaking up the thermal pad. You can see he tried a couple different designs, a couple different choices as far as the number of vias and the placement of the vias. And basically what he found through this study was that split pads reduced the size of voids and actually ended up not really impacting the percent of voiding. So in this case, because he was splitting up the pads, there was an exposed board between them, which may have contributed to the voiding by outgassing during the reflow process as well. So his next step in this process modification was, instead of breaking up the thermal pad completely and exposing the board in between, what if you just leave the thermal pad and create a similar pattern of venting channels with solder mask on top of the pad? So here was his second set of different designs that he tried out. These pathways, in the first study he tried 0.33 millimeters and 0.22 millimeters and found that the smaller one didn't have any disadvantages. So in order to reduce this area of voiding that we're choosing to have, the venting channels, you want to have a smaller venting channel, and so the 0.22 millimeters was what he used in this study as well. He also played a little bit more in this study with the via placement. So you can see here, these vias are, close to the edges of the designed areas, whereas here the vias are in the pattern, as opposed to like the full pad designs where he had fewer and more, to see what happened with those. So you can see like a few of the results over here. It's good to note at this point that we're still, no matter which pattern you're still getting more than 10% voiding, which is probably okay for some cases, but maybe not all. So we're still trying to minimize it further. And you can see that there's a large difference between the full pad designs and the broken up designs, these are triangle designs, as far as the size of the largest void. As soon as you break up that large thermal pad, you start getting reasonable largest voids. So, another cool thing to mention here, which is really important to think about, is the three different colors of lines related to insufficient printing. So he reduced like a full print over the whole pad and reduced it down to 75% and 50% to see how that impacts the voiding. And it seems to be about the same, but the thing is, when you look at the bond line and the standoff of your component, that's where it's really important. So I personally feel like maximizing the solder paste to the point just before you're starting to bridge is a good idea, so you have more material within your solder joint, so you have better reliability in the long run. So here's a little summary of the results, which I've basically told you already, but the results with the solder mask pattern on the thermal pad was much better than breaking up the pads into different sections. So I've included here a little calculation that Dr. Lee uses to calculate the length of the venting channels as opposed to the area of solder that you have. So the higher this number, the more venting accessibility you have. So the more pathways your volatiles have to get out from the center of the solder joint. And he postulates that the higher the number of venting accessibility, the better your voiding performance. But there is a caveat to this, and that's the more venting channels you have, the more voiding you're choosing to have too, because those are still going to be counted as voids. So in these studies, Dr. Lee was using all stencil designs that matched up with the patterns on the thermal pad. But even before he started working on this, there was a paper written about just breaking up the apertures without touching the thermal pad design at all. Breaking up the apertures helps to a small extent with creating venting channels. But if you're placing your component and squishing it down half of the volume of the paste, like Phil was suggesting, you might be closing up those venting channels before you even get to reflow. So stencil design can help a little bit, But in the interest of keeping the most paste under there as you possibly can, maybe this isn't the best option. I've also included pictures of some of our preliminary stencil breakups, and you can see that you're putting down so much less paste than there is area to fill. So these were less successful, but keeping the full pad in mind and breaking it up with smaller channels gives you a better result. You can also see a preliminary version of us adding preforms, adding little 0603s or 0402s to the center of the paste. This does not work very well, but I will tell you later what kind of preforms do work pretty well. So for reflow profiling, Greg put together a really good direction on the reflow profile. I've actually found that even within our family of pastes at Indium, there are some pastes that like to be heated up really fast, and they're really good when you just heat them right up. And there are some that want some weird soak somewhere in the middle. But it's really subjective, I found, as to which paste you're using, what the best possible profile is. And then in balancing your reflow profile, there are several other things to consider. You know, your other components, whether they're getting enough heat, if you have a really heavy like thermal capacity for your board, if it's a really big board, or you have places that suck up a lot of the heat, that's another consideration. Sometimes with really heavy boards, you can't do a fast ramp like some of these pastes would like to have for their best voiding performance. So we never give you an optimal reflow profile. It has to kind of go along with your paste choice and your board and the other kind of components that you have reflowing along with the QFN or bottom termination components, so that you get reliable assembly across the whole thing. So you have to consider profiling to improve your process, but it's probably not going to be the solution to get rid of all of your voiding. Another interesting option that actually Seth Homer, one of my colleagues and co-authors and stuff, was looking at is adding a flux coated preform. In this case, we're using a square preform with flux coating. The flux coating is very important if you use a preform without the flux coating. It's on top of the paste, right on the interface of the component, so you might not get wetting to your component, and that would be very bad. So using a flux coating is very important. These are square preforms in the same alloy as the paste that are about 80% of the size of the thermal pad, or 80% of the size of the paste deposit on your thermal pad. So you press the preform down into the paste, and you still have a perimeter of paste that your component will stick to, so that you prevent some of these floating kind of defects that Phil had mentioned. So the benefit of adding a flux preform, or why you'd want a flux coated preform, or why you'd want to add it, is that you're adding solder volume without adding extra flux volatiles. So in a paste, you have kind of a wet paste flux that has volatiles in it, whereas the flux coated preform has a dry flux on the outside that's maybe 1% of the weight, and it's not going to add to the volatile problem underneath the component. So this is actually kind of complex how it works, I think. But having the more dense preform with the paste helps force out the volatiles as well. So it's a further improvement if you're able to add a preform. So to test these strategies, one of our customers came to us with a test board where they had incorporated splitting up the thermal pad, patterning the thermal pad, and different size vias. I'll show you on the next slide what they all looked like. And we used a 5mm stencil because typically we found better voiding results with a 5mm stencil than a 4mm stencil. It all depends on your assembly as well. And we tested their current solder paste that they were using, which was one of ours, and our newly developed low voiding solder paste. And then we also varied the reflow profile. And in this case, we were varying the reflow profile to minimize the voiding in the QFN. We also had DPACs on this board that I won't talk about, but minimize the voiding in the QFN and also make sure that the BGA assembly wasn't getting extra voiding, so balancing those two. We also added preform, have like a little preliminary results at the end about that are interesting. So these were the patterns they had chosen. Full pad designs are on the left with different vias. Split pad designs are on the top of the right, and the masked designs are on the bottom right. Another thing about the placement of your voids and the placement of your vias and the size of your vias, these vias in this design are much larger than any of the micro vias that Dr. Lee used. So they actually gave us some anomalous results. So you can see here, this is just a plot of your total void percent for each component, and on the bottom, you can't really see what they are because this is too small, but here are the quadrant designs with 3 millivias, 2 millivias in the pad, and this is with the mask patterned. This is quadrants with no vias. And the best ones here are the full pad designs with vias. Here's the full pad with no vias, and the quadrants over here. Well, that wasn't really what we would expect from the results, right? You would expect the patterning would have had some positive impact, but instead you're seeing much larger voiding percentages with those patterns. So let's look at some Xrays. This was the original paste. This is just the full standard pad design with no vias. And you can see how the voiding is there. And then when you split it into quadrants, you can see that our Xray is only looking at one layer of contrast to distinguish between what's a void and what's not a void. So you can see it's kind of subjective here. Is this a void? Or are they going to count this as a void versus that? This is the same design, it's just a different board. So there's some subjectivity when we're looking at the actual numbers that the Xray machine spits out. Typically, in a production process, these wouldn't be a big issue because you're always running the same boards. So they're always going to have the same places that are light and dark. But in this case, since we're comparing so many different designs, you can see they all look different. There's always a different layer of contrast that distinguishes between what's a void and what's not a void. So the numerical results in this case are somewhat subjective and weren't really reflecting what we were seeing in the X-rays. Another aspect that impacts the numerical values is what the contrast is on the vias. You can see all of the vias look different. It's because the solder is wetting down into them. So it depends how much solder is wetted down into them, how dark they are, or if you can see a little light spot in the middle. And then this was when the vias are in the pathway. That's a whole different setup as far as the contrast. So the numbers are very good for these sometimes, but it's because it's not counting the voids that are actually there. So in comparison, this is with the optimized solder paste, the same sort of graph. And you can see that we're still getting the anomalous results, like the really high percentages on all these quadrant designs. But with the full pad designs, where you were seeing the lowest percentages before, it's the same patterns that are the lowest percentages, but you can see this is down below 10% for some of these patterns. So the paste is having an impact there. We're still not getting to 0. The customer was trying to get below 10, so they were pretty happy with that. This is now looking at the the percentage of the largest void. So, so this is another indication, as well as the X-rays, if you look at the quadrant designs on this side, that the largest void is very large. That's because it's counting all of the pathways as one void, instead of drawing a circle around those, and then you get 25% or something. But the smallest void, or the smaller, largest voids are very acceptable. In this case, here are the results for the optimized pace, same sort of trend. But overall, lower percentages of largest voids. And then here's just a little illustration of how we were looking at things to kind of balance the reflow profiles. So 2, 3, 4, and 5, that was the ramp to peak temperatures. This was a test board, so it wasn't heavy or anything. Like, there would have to be some consideration of your actual design before you started using a 2-minute ramp to peak profile. That would be way too fast. So you can see with the optimized paste, it kind of likes to have a quick ramp to peak, whereas the typical paste doesn't really matter what the reflow profile is in this case. In fact, that paste kind of prefers to have a little soak zone before the peak. So there wasn't a whole lot of difference between these ramp to peak profiles. Another thing you probably can't see from where you're sitting is that you can see where the voiding in the BGAs is a problem. So the BGAs wanted to have a longer profile, whereas the QFNs were doing pretty good with the short profile. So it's a balance thing. It's choosing what the right balance is. This is the pictures both Phil and Greg wanted when they were talking about collapse because you have solder wetting down the via. These are basically cross sections of a few different assemblies. This wasn't really part of the project. It was just something I was like, I wonder what this looks like. And so we cross-sectioned a few of them. And so this one is like a full pad with 2 millimeter vias. This is a full pad with 0.3 millimeter vias. And this is one where we've added the preform. So you can see here, this is 35 microns where we're shooting for 50. So this standoff isn't very good. And you can see how thin the bond line is when you look at the whole thing, as well as the way it's squeezing the solder out on the perimeter solder joint. That one happened to not be cross-sectioned where you could see the vias. This 3 mil one is cross-sectioned where you can see the vias, so you can see how the solder is wetting right down in there, not in a repeatable way. It's kind of subjective how it's going. So this is what you'll get when you don't have a tented via. And these vias are pretty big. So maybe there is, one of the questions earlier was how small can your via be to not tent it? So maybe there is some smaller via that doesn't have this happen. But in this case, since it's a plated through hole via, all of the solder is wicking away from your solder joint. And you're even getting here, the paste is squeezing out. So you're getting, when you say, Greg, that's a bad kind of thing where you have the solder going up at the edge. It's bad for reliability. Yeah, it's nothing. It's 35. So here, this happened to be what? 35 microns. 35 microns.
Under a mil?
Yeah, about a mil and a little bit. Yeah, a mil is like 25 microns. So you can see here, whereas the preform may not impact the overall voiding results, if you have a board that you have to work with that's like this, maybe adding a preform can help buoy your bond line thickness. So this is like 60, which is right in your range of the 2 to 2.5 mils that you want. So this is about 60 microns, and you can see that the perimeter solder joints up there are looking much more like we want them to look. And even though the solder is wetting into the via, you're still maintaining your bond line. So maybe if preforms aren't necessary to reduce voiding, maybe they're a good solution to promote good bond line thickness so that you can have high reliability in your assemblies. So how am I doing at time? Pretty good. So in conclusion, for voiding reduction, I've kind of shown you a bunch of different strategies really quick, but depending on whether you're a contract manufacturer or whatever, there might be some things that you can't change. You might not be able to choose your solder paste, so you can modify your stencil design. You can modify your reflow profile to optimize your process. You're never going to eliminate voiding, or at least we haven't found a solution for that yet. But you can easily pick and choose which ones of these strategies you want to put together and find the best possible solution for your assembly. And once again, the flux coated preforms, in previous studies and studies that I'm working on right now, we're showing how they reduce the overall voiding. But I think the biggest impact that they can make is in this bond line thickness, ensuring reliability and not letting your solder joints shrink away into your vias. And then I just wanted to make some notes about selecting a material, since I am a material supplier. Some things you want to really focus on, and what we're focusing on when we're developing new pastes for this application. Some things to consider: the alloy choice is going to affect your reliability. So that's one consideration. If you're having reliability problems as far as drop shock or something, there might be a lower silver sac alloy that could also help with the reliability and not impact your voiding. The flux vehicle is going to be the biggest impact on voiding performance. So there are definitely some advantages to no clean. I'll let guys this afternoon with the reliability want to talk about that as far as cleaning and electrochemical reliability. It's an important thing to think about when you're choosing a flux vehicle, but also that there are flux vehicles that are much better in voiding performance than other ones. And that's due to the types of volatiles that are in there, the type of solvents that they use. And so when we have one that's optimized for low voiding, it really means that it's a lot different chemistry than what a traditional solder paste or 2 generations ago solder paste is going to look like. And then also matching up your solder paste with your reflow profile that you're choosing. So I've got a lot of further ongoing work with this topic. We're looking into optimizing this preform thing. So how big does the preform have to be? Can you just add a small one? Is that going to have an impact? So we're playing a lot more with the geometry and size of the preform for the best possible impact. Optimizing the venting channels so you can minimize them so you're not adding a whole bunch of voiding in order to get rid of voiding. So it's also a balance thing between having proper venting channels so that your volatiles can get out, but then not making so many venting channels that you're adding to your voiding in a considerable way. And this low voiding solder paste is in the final stage of scale up and getting ready to be released, which is kind of cool. And we're moving on to further optimizing our paste to making new modifications, see if we can make it even better. And then in the future, instead of just looking at the voiding, we're noticing how important it is to look at the perimeter solder joints to make sure you've got all your connections, make sure there's no bridging because you have too much solder or something, because one side of your component's collapsing because it has vias or something. You know, there are lots of other things to look at, whereas in the past we were just looking at the voiding percent on the thermal pad. So this is, the next step is to look more at the whole assembly, and then maybe we're trying to relate the voiding performance to actual thermal performance of the component. So that would really be where you see the functional impact of what you're improving. So that's about it. Any questions? I've put my my contact info up there too if you had more questions or you wanted to get some of these papers for the in-depth results. Yep.
So can you make any comments surrounding the solder powder size or diameter in comparison to any of the voiding evaluation that you've done?
This was using type 4 solder paste. Yes, so there are going to be more oxides, the higher type of powder, like type 4, type 5, type 6. The surface area of all of the powder spheres goes up exponentially as you get higher and higher in powder types. So if you don't have to go to a higher powder type, don't. When you have more surface area for oxide to reside on, you have more requirements on the flux, and it can lead to more voiding. If you have,
you see more significant difference between the type 3 and the type 4?
Not type 3 and type 4, but if you went between type 4 and type 5, or type 4 and type 6, you would definitely see a difference. In the back with a white shirt.
So have you looked at all of other standoff devices to help with the control? So there's materials out there, primarily copper beads with silver plating that you can put into the mix to actually control the height and also maintain some of your channels as you're doing the reflow process.
We haven't looked into that yet, but that's a great idea. We don't, I don't know. I don't usually just mix copper balls in with my paste to try it out, but if we're developing a product like that, we might be able to promote something like that. But that is an option. I mean, they use copper pillars sometimes for other types of components.
Significantly to the expense too, though?
Yes. That's another big issue, and why preforms aren't more prevalent is that no one wants to add an extra placement and extra cost to their process, unless there's a significant benefit in that they have to use some design that's not ideal, and adding the preform gets them over that reliability hump that they need to get over. Yeah.
Two questions. One is, have you done anything with nano-coated stencils to see if that improves the release so you get better distribution?
Yes. I think I used, this one probably wasn't a nano-coated stencil, but I have used it in other studies. We definitely do, when I'm doing best case scenario testing for literature or something, I always use a nano-coated stencil. With a specific one, I won't say which one.
Okay, and then second is when you put a preform in, do you reduce the volume of solder paste that you're putting on the thermal pad prior to putting that preform in?
Nope, you print the whole pad. Sometimes, like with this cross-section picture, all of those stencil aperture designs were quadrants. So in that case, we just had a quadrant design and squished the preform right in there before we placed the component. When you have quadrants, you're already reducing the solder volume to a certain extent, so yes, kind of.
Since the solder flux obviously is causing the flux voids in the solder, have you looked at, and it makes up, flux you said it makes up 50% of the solder paste, have you looked at reducing the amount of solder flux in the paste as a percentage to see if that affects the voiding?
Yeah, the 50% is based on all of the other things that you want your paste to do. You want your paste to print or dispense. You want it to, connect all of your other, the 50% has been, the kind of rule of thumb for paste all along. Reducing the amount of flux is just going to make your paste really, really sticky. It's going to just change the thixotropic properties. That's always going to be a fact of life to a certain extent, unless you use a preform, which doesn't. But if you want it to be able to print and come out of your cartridge or whatever, you've got to have around that flux percent. Green shirt.
If you're running in a tin lead process and you've got lead-free components that are like that, have you guys done any experimentation on how to overcome some of the solderability issues there are that backward compatibility?
For QFN components specifically?
For QFN components, other components.
Oh yeah,
too, but
bottom
you see it
termination.
across the other ones too, so.
Dr. Lee has some papers that he's been publishing recently on mixed alloys. But I don't recall whether it was specific to bottom termination components. But if you send me an email, I can send you some papers that we've got. Yep.
Do you see any impact with like air versus nitrogen, or maybe even board finish?
It can have nitrogen versus air will definitely have an impact. I didn't bring any of those results specifically, but we can talk later about that.
Did you see the component lift off the board at all when you had the full pad?
Nope. No, it wasn't excessive, the amount of paste that was there or anything, but you do run the risk if you have too much paste. I would say I would be more concerned not about the component lifting up, but maybe the perimeter solder joints bridging. So I've seen a lot of cases where if you have uneven collapse, you can even have like the leading edge of the component have bridging and extra collapse, and then the component's kind of tilted. Is that what you mean? Like yeah. So yes, I have seen that.
On your PWB design, regarding like the venting channels you're talking about, would you recommend a particular width of that channel?
They just chose a width of that channel, and it's much larger than the 0.22 millimeters that we had researched before. So they actually moved on to another phase of their testing with smaller venting channels, smaller vias, to really take what we learned from the errors in this design and optimize them further.
They went smaller than 0.22.
Yes. Well, I'm not sure if they went smaller than 0.22. 0.22 is good. When I've talked to Dr. Lee about this, he thinks that you can go smaller, but we're still in the middle of that study to an extent. So.
Do you have any information on that?
But smaller? Not yet. Stay tuned.
We do.
Oh, you do? Okay, perfect. Talk to Greg.
We've done testing at our facility down to about an 8 mil street. And if you go smaller than 8 mils, you're going to run into a problem because it basically the venting area is shut down too fast. So 8 mils is about as tight as you want to go.
Thanks, that's good to know. Wait, share it again.
I'm still trying to understand the physics of why putting solder mask on the pad makes a channel. So it's actually a raised surface, correct? So is it a de-wetting function that happens that allows it to channelize
It prevents the solder deposits from wetting together. So this is a channel in conjunction with the matching stencil design.
So the stencil design also has to put the deposits into those and just define them.
I'm not sure if it has to. I'm working on whether it has to, because this one, they were broken up the same way. But I actually think maybe if you print, do you have an opinion on this? If you print over the solder mask, that they might de-wet and create the channel during reflow.
We've never seen anybody printing over the solder mask.
Yeah. Have you looked at solder mask patterning like this?
Yeah, we have. We don't like it.
You don't like it?
No.
Okay. Well, there you go. Anyone else?
We'll have to cut the
Oh, cut it?
question. So,
Lunchtime?
So yeah, make sure that you catch up with Brooke and the other speakers over lunchtime, which we will start now. Brooke, thank you very much. Here's a little something from
Thank you.
us. So the program is we have